Hello everyone, my name is Jose Martin-Garcia, and today I'm going to be presenting the core language part of new in version 12. So this area introduces in every version of Mathematica a variety of new functions that can be used in multiple situations and in different contexts. This time we have 4 rows to present and talk about today, and they are organized in the following way. First, we have a row of functions dedicated to functional programming, and we will see the new function carry, here the new function SubsetMap, the new function TakeList, and find repeat. Then we have a row of functions dedicated to text manipulation, and we will see how to find synonyms and antonyms, how to capitalize words, translations, and how to use nearest in a new way. Then we have a row of functions dedicated to numbers and order. We will see different or new ways of presenting numbers and of handling order in lists of numbers or other expressions. And the final row is dedicated to a new construction called Numeric Array. This is a new construction that allows us to store in a more compact way arrays of numbers of a given type. We will see later how it works. Here at the end, we see many functions, all added in version 12, related to what we have just explained. And there are guides and links, like link to a talk during the last Wolfram Technology Conference on how to use numeric arrays, etc. So as with other Twitch sessions in this series, we will be evaluating some of the examples in this page and explaining how the functions work. So let's go with carry. So the idea of carry is using the Wolfram language functions in a new way. This is a very flexible way. So traditionally, in the Wolfram language, functions can have several arguments. Carry is a way of making those functions of multiple variables functions of only one variable. So we pass a variable at each time. So let's see how this works. So we have examples with the so-called operator forms, but carry is in some way a super operator form that allows us to express any function as an operator form. Take, for example, carry with a single function f. What this means is that rather than using f as a function of 2 arguments, we will be able to use it with 1 argument, then it stays there. And if we pass it a second argument, you see, it will flip them. So this is the standard behavior of most of our operator forms. They take 2 arguments and they treat them in reverse order. So with carry, we can also say, okay, I'm going to have a function of 3 arguments. Then it will wait with the first and the second argument. But once we provide the third, it evaluates the function. This is quite useful. Imagine, for example, that we have many functions that we are going to differentiate with respect to x. We may want to have, for example, carry of dx. So this is our new function. And now we can say, okay, I want to differentiate sum of x. There you have it. Or we want to differentiate tangent of x, etc. Right? So this is quite useful. And in this way, we can make, as I said, functions that do not have an operator form, say D, be operator forms. Example given in the page works with dot. And here we see how we are making dot a function of 1 argument, which is going to be the matrix. right? And then that function, mat1, can take single arguments, which are the vectors. So as I said, this generalizes the concept of operator form and allows us to have operator forms of any other function. Okay. Let's go now to another interesting function called SubsetMap. The idea of SubsetMap is to operate on subsets of a given list. So take, for example, a list like A, B, C, D, E. So now what we can do with SubsetMap is to say, for example, subset map of this list. I'm going to use accumulate. And I'm going to operate on positions 2, 4, and 5. So what's happening here is that it's taking elements of at positions 2, 4, and 5, namely B, D, and E. It's computing accumulate of them, B, D, and E. And then it's inserting them again at the same positions, 2, 4, and 5. So we have B at position 2, then we have B plus D at position 4, and B plus D plus E at position 5. So this is a very flexible operation, and the example we give here is the following. It's a so-called sorting network. So what this is doing is the following. Let's start with the reverse list of numbers 1, 2, 3, 4. So 4, 3, 2, 1. And now this random network will find a path in which we flip, for example, in this case, we flipped pairs of numbers. In this case, 3 and 2. So they became 2 and 3. And then from this stays. So this can happen. It doesn't find a pair. Well, it doesn't find. It's generating individual random pairs of swaps. And if this gets their list more sorted, then it's accepted. If not, it's not accepted. In this case, it's flipping, for example, 2 and 4, etc. So now, with this command, that now, we get what was happening. So we started from 3, 4, 2, 1, and you see how, for example, here we flipped 2 and 3. Then later we were performing other flips until we ended up with precisely the reversed. 1, 2, 3, 4. If we do this for a larger case, like we start with 30 rather than 4, it takes longer, more steps to organize, to sort the list. And this is what we get now. And you see how most of the action happened at the beginning. Here it was very easy to find swaps that would sort the list, but then it gets slower and slower and slower. And at the end, it takes a long time to find the last one. This gets clearer if we present it in a logarithmic way. Right? And we see now how the action happens in this part, this intermediate part. Okay? So that's a subset map, a way of mapping functions over subsets of elements. The next example is another very interesting function called TakeList. TakeList generalizes partition. And so if we start, for example, with alphabet, the whole alphabet, 26 letters of the alphabet, now we say take iteratively first 1, then 2, then 3, you see? First 1, then 2 elements, then 3 elements, 4 elements, etc. We don't need to go to the end. We just take the elements specified by this. So as I said, this is a generalization of partition. Partition would be able to take sublists of all of the same length. This works also with matrices or deeper arrays. For example, we construct this matrix. It's a 5 by 6 matrix. And now we are going to say, okay, the dimension 5 is going to be partitioned into a group of 2 and a group of 3. And then the dimension 6, the second dimension, is going to be partitioned into 2, 2, and 2. We get this result. Because we are partitioning a matrix and we are partitioning both its dimensions, then we get something of depth 4. It's quite difficult to see what's going on here, but if we map this result, if we format this result using matrix form, then we get that, which is clearer. Right? We see how this dimension was partitioned into 2 and 3, and this dimension was partitioned into 2, 2, and 2. We want to go back to the original array, we just have to use array flatten. And this converts this object into the original object. Okay, this example is quite interesting. So what we will be doing here is computing the dates of the Easter Sunday in the Julian calendar. Recall that the definition of Easter Sunday is different in the Julian calendar and in the Gregorian calendar, our civil calendar. So here we will be using the Julian calendar. So this function, for a given year, computes the, let's do it here, computes the date of Easter in the Julian calendar. So for example, for year 2019, we find that Julian Easter was 15th of April in the Julian calendar. That's very important. So if we convert that date into the Gregorian calendar, we see that it was actually Sunday, April 28th. Okay. So what we are going to do here is to compute the dates of Easter Sunday for 10,000 years, from year 1 to year 10,000. We got that. And now we are going to use find repeat to see if the list repeats. And it does. It repeats every 532 years. We can, for example, take a single cycle, the first 532. It doesn't matter because we know that it will keep repeating. And now we move all of them to the same year, just to use date histogram, and we compute a date histogram. We see how they all go from March 22nd to April 26th. And remember, this is in the Julian calendar. We see this trapezoidal shape. We had computed these using the Gregorian calendar, we would have obtained a similar, it's a bit more complicated in the case of the Gregorian calendar, but we get a similarly looking trapezoidal shape. Okay. Let's go to the next example. Yeah, so that was the row dedicated to functional programming. Now let's go to the row dedicated to text manipulation. We have here a new function called synonyms and another one, antonyms, which for a given word, it will find synonyms and antonyms in our list of words in English. So this is an example for functional, synonyms of functional, and antonyms of functional. What we are going to do here is, starting with the 8 longest words of the Gettysburg Address, which are these, we are going to iterate the finding of synonyms. So we start with each of those words and we find their synonyms, and we find respectively 4 words, here also 4, 3 for the second one, for the third one, 13 for the fourth one, etc. Now we iterate again for each of those and put them together. And so we find now 35. And we iterate again for the synonyms of these 35 words, put them together, we find 145 again and again. So we iterate 7 times and we see how this grows. And it grows exponentially at the beginning. That's why this looks roughly linear in a log scale. And at the end saturates. And this saturates because of the size of our list of words, which is roughly of the order 100,000. But you see how fast the network of synonym words grows. Something funny is that if you start with a given word, like in this case we chose dead, and you compute synonyms multiple times, at some point you will end up finding a word that also belongs to the list of its antonyms. In this case, we have found life, for example. Okay. Capitalization. We have also new words dedicated to capitalization. And we have several types of capitalization schemes. Text copy, we call it capitalize. So, for example, in this first case, we have the all words scheme, which means capitalize all words. Or we have the scheme long words, which will capitalize string, for example, but not other words like is or a. This is a longer example showing the 4 possible schemes we have for capitalization. And what this example will do later is to go to collections of book titles, and compare what our function would have predicted in the case of title case with the capitalization that they actually got. So, for example, this is showing in red the differences that we found. And for a bigger collection of books, in this case, nearly 3,000, this is showing what we call the edit distance, which is the number of changes from what we found and what the book had. So for most cases, we find edit distance 0, which means the book is correctly capitalized. The title of the book is correctly capitalized. We found this number, few hundred, in which there was 1 change, this number, a few tens, 2 changes, etc. And at the end, this shows the 5 cases with more changes. Again, in red, we show what we think shouldn't be capitalized, but was capitalized in the title, in the book titles. Okay. We have a new function called text translation, which is able to take texts in other languages and translate them into a given other language. For example, in this case, it's able to realize this is Japanese, and so it translates into English, or in this case, it's translating this sentence into these other languages, Russian, Japanese, or Spanish. We can use this function as cloud deployment. Or in this case, what this is doing first is using text recognize to extract a text from a given image. And then this text, which is in English, is being translated into Spanish. Or for example, here we have a tweet by Steven being translated into Spanish. The last example in this row shows a new way of using the function nearest. So nearest is a very powerful function that can find for a given object what other object in a given list is closer to it for a given chosen distance. For example, let's take the list of words we have in French, which is more than 100,000 words. And yeah, nearest is going to find the nearest 5 words to this one in our list, and they are these. This is the standard way of using nearest. The new way of using nearest uses this notation, which is words go to a list of properties we want to get. If we say all, we get all the possible properties, like the element, the actual words we found, the index, meaning the position it was found in the list of words, and the distance. Of course, we find the word itself at distance 0, and then we find other words that look similar, and so they have increasing distances. This way of using nearest has also been extended to other functions, like, for example, take largest by. Again, we are saying, give me the properties element and index based on string length, the first 3. So we are finding here the 3 longest words in the list of French words, and we get, respectively, the word itself and the position in the list. So this is a very flexible way of making a function that existed before report even more things than it was reporting before. Okay, that concludes the second row dedicated to words. Now let's go to the third row dedicated to numbers and order. So we have decimal form in version 12. Decimal form is a function very similar to number form, but what it's going to do is to guarantee that we always get numbers in decimal form. Namely, we never see scientific form or any other of the numeric forms. The example we have here is, well, let's do first a small example. Imagine that we have a very large number, like that. So by default, because it's larger than a million, it's going to be presented as in scientific form. But if we use decimal form, it will be presented in decimal form. Okay. Let's go to our example. Here we are taking the first 12 ellipsoids given by geodesy data. Each of them has a number of properties, and in this case, we will be working with the semi-major axis, the semi-minor axis, and the mean radius, some sort of mean of these values. So a nice way of presenting the information is to compute geodesy data for each of the spheroids and each of the properties, and then we say, well, present me the results in a table. So that looks nice, but you see, it looks kind of misaligned. So a simple way to avoid that is to say, well, give me all the numbers in decimal form. Here we have them. And you see they all now look, I mean, they all have the same structure. We can also write this in a different way. This was using composition, but we can use functional language to do this. And now we can also say, give me all the digits you can, but I want 2 digits after the decimal point. And we see how it adds 2 digits. So we have now precision to the centimeters. Okay, so this decimal form is very useful when you have to present numbers in a consistent way. Let's now go to another alternative way of presenting numbers, which is percent form. The same idea, we start with a number, let's say 0, 2, 4, 5. Percent form is going to write that number as a percentage, like that. Very simple. The example that we are presenting here is, well, let's first start by computing numbers that make sense expressed as percentages. So what this does is extracting the radii of moons, of planets, and then computing the size of those radii as fractions of the radii of the respective planets. And yeah, so here we have the planet. So for a given planet, we get its satellites, compute the radius as an association, and then divide by the radius of the planet itself. And so for Mars, which has 2 satellites, Phobos and Deimos, we have those numbers. By using percent form, we compare these results for Jupiter. Jupiter has many more moons, but we say, okay, give me up to 4. We get those numbers and expressed as decimals, as percentages, they look like this. Or now we can do the same thing for all the planets, and including Pluto, which is a minor planet, which have moons. And we take, again, up to 4 of them. Right? So for the Earth, we have only our moon, and we see how large it is, right? 27%, while in other cases, it's typically a few percent at most. So the moon and Pluto, which is 51%, are the 2 extreme cases. All other cases are under 10%. So that's interesting. Well, we have seen 2 ways of formatting numbers. Now we are going to see some additions in the ordering functions, in particular, ways of ordering numbers. Let's first remind ourselves what ordering functions are. This is a very useful concept. For example, let's take words. And we can say, okay, let's put some words like what could we use? Yeah, I'm going to use this word in Spanish. So I now need and tilde. Okay. to do that. Okay, so I have these two words. Now, if I do sort of this list, it's sorted. If we do it in reverse, no, I'm going to change this, sorry. Yes, so here we have the way in which we can order this list. A possible way to alter the order is using a different ordering function, which is alphabetic order, which will allow us to say, okay, use the rules of ordering words in Spanish. And now you see how in Spanish we order this in a different way, because we want to use always N before this letter that we call ñ. While if we use the English of rules, it will treat N and ñ as equivalent, and because this is A that comes before O, then it will place them as we were seeing before, this word before this one. So ordering function is a way to determine a basic order in which we want to sort things. So we have other ways of sorting, for example, numbers. Let's take, this is quite useful. Let's take, for example, 1 and minus infinity. If we use canonical order prefers shorter things, smaller things, before larger things. Larger in the sense of how they are expressed internally. So it's going to place 1 before minus infinity, which is typically not what we want. So now we can say, okay, use numerical order. Numerical order knows that minus infinity comes before 1. Okay, so sort always had an ordering function argument. So what we have done in version 12 is propagating this ordering function argument to other places. For example, sort by. Sort by. Sort by. Let's look at the documentation. It always had this function f argument, but in version 12, we have added this new syntax, which takes both the function f and the ordering function argument p. This means that after applying f to the elements of list, they will be sorted according to the ordering function p. So here we have an example. We take a list of tuples, and we say, okay, let's plot them. So we have all these points. Now, how would we sort them? Well, we are going to sort them by norm. Sorry, copied the wrong one. We sort them by norm using canonical order. See, there is no third argument. Now we get the canonical order, and we have here the same type of problem we found before with infinity. You see how 5 is being sorted before square root of 2, because square root of 2 is a larger expression than 5, which is just a number. So this makes 5 be before that, and it generates this kind of not very clear plot. Now, let's use them. Let's sort them using numerical order, and we get that result. Now, if we compute the norms, we see how now they are truly ordered properly, numerically. And to see that, we can plot the result, and we see how it would start here, then it goes to these two, then there, then these two, then these two, those two, etc. You have to think of this. Probably it's clearer if we use aspect ratio goes to 1. You have to think that we have circles all coming from the center, and we are first on that circle, then on that circle that goes through these 2 points, then on that circle that goes through this point, then on another one, then this one, etc. And so that's why we are moving farther away from the center. So the conclusion is that this operation was correctly performed only when we specified here that we wanted to sort the norms using numerical order. That's an important observation. Okay, let's go to the final one here, which is called reverse order. Reverse order is another handy function when it comes to sorting expressions. A particularly useful case is the result of tally. Suppose that we go to country data, we get all 250 or so countries, and we compute the continents of those countries, and we get this result. Okay, now the question is, well, I'm most interested in the largest case, which is Africa. So how do I do that? Well, if we do sort by this expression last, we get them sorted, but in increasing order. So the question is now, how do I sort them in reverse order? Well, we have now the function reverse sort by, which is going to sort them as we wanted, presenting first the cases with the largest number of countries. Reverse sort by is effectively like applying reverse to the result of sort by, but sometimes when there are ties and some of the results have the same values, it will do things slightly different as determined by the third function. Remember, we have now an ordering function argument. Another case in which reverse sort by is quite useful is when manipulating datasets. If we take this dataset of values of data for planets, we can now, for example, use this query construction saying, give me the dataset in which the rows are reverse sorted by radius. And we see how now radius are decreasing because they are reverse sorted. Okay, and now let's go to the final row dedicated to numeric array. As I said, numeric array is a new construction in version 12, which allows to store arrays of numbers in a very compact way. For example, let's take a look at this case. We start with this array of numbers. It's 200 random integers between -100 and 100. And now we convert it into a numeric array using integers of only 1 byte. Now, this means that the size of the array itself is much smaller. If we compare the array, the original array, it has this size. It's effectively the 200 numbers multiplied by 8 bytes. It's 1, plus a bit of overhead of the representation of the structure. Here we have the 200 numbers, each one being using a byte, so that's the 200, plus a bit of overhead again with the representation of the structure, 96. If we take a bigger case, say like that, we see again how now we have 20,000 numbers, which correspond to 20,000 bytes plus the 96 of overhead. And here we have again multiplied by 8, 160,000 plus the overhead of the structure. So you see how there is a large gain in size there. Numeric array is able to take arrays in any form, like sparse arrays, and then many of the functions in the system can already take numeric array objects and manipulate them as if they were normal arrays. The next example is actually dedicated to integration of numeric arrays in the system. Here we have a numeric array, again, integers of 1 byte and 200 of them, and the standard basic functions to manipulate arrays or to report properties of arrays can work with those type of arrays. So the dimensions of that array are 10, 20, the depth, so the number of lists we have is 2, the length, which is the first dimension, is 10, etc. The plotting functions can understand them, as we saw before, and some other manipulation functions like most, on part, join, etc. can take numeric arrays and keep the structure as a numeric array. In case you find a function like a totally generic function f that cannot handle them, then what you have to do is to apply normal that converts the numeric array into a normal list, and then map will happily map f through the elements of that array. Okay. And then the final two examples, which I'll show here in the web page, show the integration, further integration of numeric array in the system. This example in particularly shows how numeric array is integrated in library link. So you can write your own library link functions, and this is an example of how they look, and then compile them into libraries that you can call using library function load. And now those library link functions will be able to take directly numeric arrays. In this case, we have a function that is going to compute the complex conjugation of the numbers in an array. So we construct a numeric array, this one. It has 3 numbers of type complex 64. And if we normalize the array, we see the numbers, but our functions can actually compute the complex conjugation of that numeric array, return another numeric array, and now we normalize it to see the result. And you will see that the numbers have been correctly conjugated. And this is another example in which we import some data into a construction called byte array, which is a very close relative of numeric array. And then just by importing it, we see what was inside, which was this object. Very good. And the final example is dedicated to show how the fact that the numeric arrays can be stored in a much more compact way in memory also allows for faster imports and exports. And this is the particular example in which it's comparing the gain in version 12 with importing numeric arrays. And so we see how it takes half the size in memory and also almost half the time in importing the object because it's smaller. Okay, so that concludes the presentation of the examples in this web page dedicated to the addition of core language functions into Wolfram 12. Thank you very much for your attention. And if you have any questions or comments about these functions, don't hesitate to contact us. Thank you very much.